So polynomial f over this field capital F, where characteristic of f is 0, is solvable in radicals if and only if its Galois group is solvable. So now we show in this direction. So we will show that Galois group of a polynomial is a quotient of a solvable group, and we have shown that the quotient of a solvable group is solvable. Therefore, the Galois group of the polynomial will be solvable. So the strategy is to construct, say, a field E in which f will split completely. So if f splits completely in this field E, then this field E contains the splitting field for f, and we will show that this Galois E over f is solvable. So therefore the Galois group of the polynomial, which will now be the quotient field of this Galois group E over f, because the splitting field of f is contained within this big field E. So G of f is a quotient of the solvable group, this, and this will show that the Galois group is solvable. So all we have to do is construct E a splitting field for f and show that the corresponding Galois group is solvable. So again, recall what does it mean to have solvable by radicals. So that is, you have a tower of field extensions like this. You construct fi plus 1 from fi by joining alpha I, so that alpha I to the power of ri lies in fi, where we said that alpha I is a root here. So obviously you basically inductive construction, and some power of alpha I lies in the previous one, and then this k is the splitting field of f. So this is given to us. We are saying solvable in radicals. So again, recall our most important step is the cyclic extensions, which make everything possible. So cyclic extensions are of the form f alpha to the power of n is in f, and f also contains the primitive root of unity. So this is what makes things possible. So this is extremely important to remember. So before we go any further, recall what a composite of two fields mean. So say we are given two fields f1 and f2, and the composite of two fields would mean that you have to find a bigger field E which contains both f1 and f2, and then intersection of all subfields of E which contain both f1 and f2 is the composite of these two fields. So again, composite of two fields f1 and f2 which is contained in some bigger field E is the intersection of all subfields of E which contain both f1 and f2. So an example would make the situation more clear. So the example is composite of, say, root 2 adjoint to rationals and 2 to the power of 1 by 3rd adjoint to rationals is 2 to the 1 by 6. So because this will contain this also and this also, so take the third power of this and the square of this, things would be clear. So now we want to use this definition of composite of two fields further. So say you are given H as a subgroup of group G, and group G is the Galois group of E over F. So group of automorphisms of E which fix F. Now in group theory you can see that you can get a largest normal subgroup contained within H. So largest normal subgroup contained within H is just this intersection of all the elements of sigma and G, and then you have sigma H, sigma inverse. So this N is the largest normal subgroup. So it is a subgroup of H, but it is also normal. So it is the largest normal subgroup which is contained in H. So in the fundamental theorem of Galois theory, we showed that between this and sigma EH you had 1-to-1 correspondence. So this EH were all the elements of E which were fixed by H. So there was 1-to-1 correspondence like this. So this En now corresponding to this subgroup N, you also have a field En. So what is this En made of? So En is again this sigma EH is there, corresponding to every sigma here. You take a sigma here, you have a sigma EH. So En is just a composite of fields sigma EH. So intersection of all subfields of E which contain both. So you're saying intersection here. So it is composite of all these fields sigma EH. So we talked about these fields in the lecture on fundamental theorem of Galois theory. So this En is called the Galois or normal closure of EH. So Galois closure and normal closure mean the same thing. So we had given examples of normal closure before. So the important thing is to construct such a normal closure, you need to take composite of fields of this form, sigma EH. So this is important. So to construct a closure, you need composite of fields, and this is what we are going to do to prove this result. So now we have copied this here. Fundamental theorem of Galois theory showed us there was one-to-one correspondence here, and this En is made up of composite fields like this, and this En is the Galois, the normal closure. So whenever we have this Galois or normal closure, it will be made up of composite fields like this. So now you set n as R1 times R2 all the way to Rn. So because we already have this portion, so this portion we have that the polynomial is solvable. So we have this portion. So now you construct this L. This L will contain K, but this will also contain zeta, the primitive nth root of unity. We have no option but to include zeta because we want to use our magic bullet right here. Cyclic extensions of the form like this, where f contains primitive root of unity. So since we want to have cyclic extensions, which is the only way we can get solvable groups, therefore we need to have this zeta adjoint to L. So then this K over F, this K over F is a Galois. This is Galois, and this is because it corresponds to, say, polynomial hx times xn minus 1. So this xn minus 1 obviously corresponds to zeta, and this h of x has, say, a root rho, and you can set k as f of rho using primitive element theorem. So this is kind of obvious, the way you construct f0, f1 from f0 is you take f0 and you adjoin alpha 0 to it, and some power of alpha 0 lies in f0. So f2 would be, you take f0 alpha 0 and then alpha 1. So this is our f2, and some power of alpha 1 lies in f1, and your fn obviously now is f0 alpha 0 all the way to alpha n minus 1, and you can see alpha n minus 1, some power lies in fn minus 1. So basically this fn is of this form, and by primitive element theorem you can ignore all of them and just write one element. So f0 with rho, f0 is just f, so that's why we are writing f of rho using primitive element theorem. So let E be the Galois closure of this zeta attached to K. So then E is generated by composite fields. Now we are using this result. We are using a Galois closure, so we have to use composite fields. So zeta is the root of this, and then the rest of the roots are like this. So this zeta belongs to a different irreducible polynomial, so we are not making sigma act on it. So you're leaving this alone because this is not part of our polynomial here, and sigma acts on the rest of the roots like this. So sigma you're taking from the Galois group. So you have sigma alpha 1 all the way to sigma alpha n, then you have sigma 1 alpha 1, sigma 1 alpha 2 all the way to sigma 1 alpha n, then you will have sigma 2 alpha 1, sigma 2 to sigma 2 alpha n. So you have so on. So all these will generate E, and this E is generated over F. So this is generated by these elements over F, over our field F. So obviously by themselves they will not generate a field, so they are generated over F. So basically we are using this result, you are using composite. So the sigma is precisely what is acting here. You're taking all the sigmas in the group. So now you adjoin them to your base field F. You start with F. So you say, we are constructing this composite field. So basically you're going to adjoin all of them to F here. So F, you first adjoin zeta, then alpha 1, then F zeta alpha 2, so on. Then you start adjoining this these, everything here. So at every step you're adjoining to each fi, whether this is this or something here or here. This is obtained from the previous one by adjoining the rth root of fi minus 1. So f2 is obtained from f1 by adjoining some sigma 1 something, sigma 1 alpha 2, or say sigma 2 alpha 3, something like that. But even if you apply sigma to the root, it is still the rth root of something, because that's what we have. You have the root of some polynomial here. So here r could take any of the values. R could take value r1, r2, anything, or even n, which is product of all these values. Now each of these extensions is abelian. In fact, other than this extension, every extension here is cyclic, because you are basically adjoining a root of this form. Alpha to the power of something lies in f, because this alpha 1 itself is taken from here. All these alphas are precisely these alphas which are getting carried here. So each of these extensions here is cyclic, except this first one. So this may or may not be cyclic, but this is abelian. So each of these extension is abelian, and possibly all of them are cyclic except the first one. So this is our extension which might cause a problem. So that's why we are using abelian and not cyclic, because this might not be cyclic. But we have abelian, and we have defined our solvable groups in two ways. We have defined the quotients as cyclic, and we have defined them as abelian and showed that they are equivalent to each other. So each of these extensions is abelian and cyclic. Possibly the first is not, possibly. So the Galois group of this fi over fi minus 1, this is precisely gi minus 1 over gi. So now corresponding to every field you have the corresponding Galois groups, and therefore this is solvable because this is cyclic. We are saying this is cyclic, or it is abelian. So rather than taking cyclic, just take abelian, and then you have, each of these, you can form a chain of groups like this. Each of them is a normal subgroup of the previous one, and their quotients are abelian. So therefore you have a chain corresponding to every extension here, corresponding to any extension here, you have a chain which will form like this, and therefore your Galois group is solvable. Notice for every extension actually comes from a radical extension, comes from a polynomial precisely of this form, because adjoining sigma will not change your polynomial. It is just going to permute the roots here. So it is just going to change the polynomial somewhere, but you still have the polynomial. So we have been able to prove that Galois E over F is solvable, because you can have groups like this. So we have been able to prove this result.